Hello, welcome to my tutorial on Hooke's law. So, Hooke's law says that extension is proportional to force. So, it can be written as F equals KE. So, if a metal wire with a weight attached to the bottom stretches, then the weight is pulled down with a force F, and it produces an equal and opposite force at the support. So, Robert Hooke discovered this in 1676. And the extension of a stretch wire E is proportional to the load or force F. This relationship is now called Hooke's law, and K is the stiffness constant. So Hooke's law can also apply to springs, but first we'll have a look at the generic diagram. So this is the force F that I was talking about earlier, and the force F is equal and opposite of both ends. The natural length is, well, what the wire was before I started putting the weight on it, and the extension is how much it has stretched by according to the stiff constant and how long the extension actually is. And it also applies to springs. If you take a look at the bottom left, the extension or compression of a spring is proportional to the force applied. So Hooke's law still applies. There are tensile forces to stretch the spring and compressive forces to squash the spring. So for a spring, K is the same value whether the forces are tensile or compressive, and it's not true for all materials. However, Hooke's law does stop working when the load is great enough. There's a limit to the force to apply for Hooke's law to stay constant, and the graph shows load against extension for a typical metal wire. The first part of the graph shows Hooke's law being obeyed. There should be a completely straight line, as there is a linear or straight line relationship between load and extension, and when the load becomes great enough, the graph starts to curve. The point marked E on the graph is called the elastic limit, and if you increase the load past the elastic limit, the material will be permanently stretched. When all the force is removed, the material will be longer than at the start. Metals generally obey Hooke's law up to the limit of proportionality, which is really near the elastic limit. But you've got to be careful. There are some materials like rubber that only obey Hooke's law for tiny extensions. So if we have a quick think about rubber, if I did decide to yank a rubber apart, then I would be able to stretch it apart. Forgive me that it looks more like a peanut, but when it breaks off, this is at its maximum extension. When it stops obeying Hooke's law, when it breaks, it will stop obeying Hooke's law, as there is no longer that straight line relationship. But we'll learn more about this later, and I'll talk about why it happens and what words to use. But for now, a straight line relationship between load and extension must happen in order for Hooke's law to be obeyed. So plastic is meaning that the material becomes permanently stretched, and atoms in the material move position slightly, and it's relative to one another. When the load is removed, the atoms do not return to equilibrium positions, and a metal stretched past this elastic limit shows plastic deformation. Now, this is actually what the rubber will start showing once it's pulled apart. And elastic deformations, the material returns to its original shape once all the forces are removed. When the material is put under tension, the atoms of the material are pulled apart from each other, atoms that can move small distances relative to the equilibrium positions without changing the position in the material. Once the load is removed, the atoms return to the equilibrium distance apart. So elastic and plastic are both the two types of deformations that you have to appreciate as you go on to do physics. So we'll have a look at a question now. A metal guitar string stretches 4 millimeters when a 10 Newton force is applied. And if the string obeys Hooke's law, how far will the string stretch with a 15 Newton force? We need to calculate the stiffness constant for this string in Newton meters. And the string is tightened beyond its elastic limit. What will be noticed about the string? So this is a 1 mark answer, this is 2 marks, this is 1 mark. And for this question, a rubber band is 6 centimeters long. When it is loaded with 2.5 newtons, its length becomes 10.4 centimeters. Further loading increases the length to 16.2 centimeters when the force is 5 newtons. Does the rubber band obey Hooke's law when the force on it is 5 newtons? Justify your answer with a suitable calculation. And whenever the board say this, you need to write the calculation out with full workings in order to get the 2 marks that is on offer to you. So I'll give you a 5-second pause and we'll have a look at it in a bit. Okay, hopefully you had a look at the questions, so now we'll quickly run through them. So force is proportional to extension. The force is 1.5 times greater, so the extension will also be 1.5 times the original value. That is 1 mark. The extension is 1.5 times 4 millimeters, which is equal to 6 millimeters. And for part B, F is equal to KE, so K is equal to force over extension, which is 1 mark. So if K is 10, and you put that over 4 times 10 to the minus 3, this is equal to 2,500 Newton meters, or rather newtons per meter. So the string now stretches much further for small increases in the force, and when the string is loosened, it is longer than at its start. And when the rubber band does not obey Hooke's law, it's because when the force doubled from 2.5 newtons to 5 newtons, the extension increases by a factor of 2. It's not 2.3, it's actually just 2 times. Absolutely ridiculous. But yeah, you get the idea. So what we learnt today was that Hooke's law can be obeyed by metal wires and metal springs, and it stops working when the straight line relationship between load and extension stops and it reaches its elastic limit. We also learnt about the elastic and plastics deformations and how they are different. So I hope you found this tutorial useful. Like, comment, subscribe, favourite, even message me. I have got a message from a very keen subscriber, so I'm quite happy about that. This kind of interaction is what I'm going to need in order to progress any further on the YouTubes. So thank you very much and goodbye.